Good evening or good morning to those of you in the far west. So my name is Nils. We're going to talk about LHC at home on behalf of the LHC at home team. There are many people, many scientists behind, and also many people who have worked on the computing part over the years. So quick introduction to Cern and what we do at Cern and simulate with LHC at home. A few words about our applications, some statistics, and a few words about our survey infrastructure. So Cern is the European Organization for Nuclear Research, more known as the European Laboratory for Particle Physics. We are outside Geneva, on the border between Switzerland and France, in the countryside. We have them. We are funded by 23 European member states and also partners all over the world. Under normal times, there are more than 10 to 12,000 scientists at CERN, but now at COVID times, they're working remotely. So we have the Lhc Accelerator about 100 meters below ground in a tunnel with 27 kilometers of circumference. And then the smaller accelerators, so the SPS with 7 kilometers of circumference, and the PS and so on, and the actual proton source that starts first there goes into a linear accelerator, then into the booster, then to the PS, and gets accelerated around. So to get high energies, we have strong magnetic fields, and the Lhc magnets are actually cooled down to 1.9 Kelvin, so minus 271 degrees. This is done with liquid helium and so on. And then we have 4 big experiments, detectors around the LHC. So we have ALICE, ATLAS, CMS, and LHCb. Just to give you an idea of the dimensions, so ATLAS here under construction, 7,000 tons, 100 million sensors that generates data 40 million times per second. You see a chap down here. It's like a cathedral, actually. Here a screenshot from an event, candidate event for the Higgs particle discovered by ATLAS detector. Here we see the CMS detector and the maintenance. Here you see the wheels with the electronic modules. And a screenshot again from CMS. So these collisions, they produce when an accelerator is running 1 petabyte per second. So it's way more than we can ever analyze. So there are hardware and software triggers that filters data down to, let's say, 10 gigs per second after the latest upgrades. This has to be analyzed. Even these data quantities, that's far too much for a computer center. At CERN, we have a fairly big computer center, but we can only handle about 15% of the capacity. So to analyze all the data from the LHC, we have a grid. David Anderson mentioned the OSG, Open Science Grid earlier. We have the Lhc Computing Grid that also has OSG as members to analyze data from the LHC, and that's many sites all over the world. So then you can ask, why volunteer computing at CERN? Well, actually the Lhc Computing Grid has limited resources. It's fully committed to LHC data reconstruction and analysis. Even now, when the accelerator is down for upgrades, we are analyzing data sets from last years. You may have read in the news that there were discoveries from the LHCb experiment that had new questions to the standard model, same from ATLAS. We need a lot more computing capacity for simulations. We need to simulate how to do better quality beams in the accelerator. We need to simulate how to build better detectors and improve them. So for this, we can use volunteer computing. LHC at home is our volunteer computing project. So it started as a BOINC project in 2004 for the 50th year anniversary of CERN. Before that, it was actually running as a screensaver project on desktops at CERN with a CERN screensaver, CPSS, for a few years. So LHC at home started with a 6-track application for beam simulations, and that's our main applications even now. From 2011, we expanded when we had a possibility to add virtual machines with physics event simulations, so theoretical models of what happens in the experiments. And later on, also experiment applications to simulate detectors running in virtual machines were added. So the applications on Lhc at home, so it's 6-track, I'll come back to it in a moment, for particle beam simulations. We used to run a few years Garfield for simulation of gases detectors, but this app is now obsolete. We have a theory application, Atlas, the Atlas experiment. LHCb running for a few years. It's now paused, but it will probably come back. And also CMS for the CMS experiments, at event simulations for the CMS detector, running on a virtual machine in VirtualBox on Linux, Mac, or Windows. All our applications on Lhc at home are currently CPU applications. Few words about 6-track, as mentioned by Marcus in Australia. Yes, by running 6-track and helping us tuning the beam of the accelerator, you ensure that the protons don't get lost, that they don't go out of the beam pipe. Actually, those who have been running 6-track have maybe seen that some of the application runs are really short. These are particles that get lost. So it's used by the accelerator team to study the characteristics of the particles going around, and they have to go around many turns in the LHC, in the beam, to get high energies, and we have to keep them in place. So it's really for tuning. 6-track is a single executable built from Fortran sources, so it's a very small executable. It's available for Linux, Windows, Mac, Android, and FreeBSD. We have as for Intel and also ARM. Currently, we only have CPU versions on Lhc at home, but there's another version of 6-track or variant of 6-track that can run on GPUs, so it's potentially interesting. And really, thanks to the Lhc at home volunteers, far more computing capacity has been available for 6-track than what we could host at Cern, and it has really been helpful for the beam quality of the Lhc. So some words about the Atlas application from my colleague David Cameron in the Atlas experiment. So the Atlas application runs simulations of particles produced by the collisions inside the Atlas detector and interacting with the detector. The simulation code runs only on Linux, so there are two apps. There is one that runs VirtualBox, with the Cern VM, the virtual machine, for Windows and Mac, and then there's a native Linux application using containers that requires CVMFS, which is the Cern VM file system, and HTTP file system on the host. This file system lets you pull the software via content delivery networks and so on to the volunteer computer. My colleague Lawrence will talk more about that next week. So like the experiment, the Atlas app is large and complicated. It's a huge image, so it takes time to download it, and you need at least 4 gigs of memory. Thanks to BOINC volunteers and also occasional backfill from grid sites, Atlas gets 10% of the simulation capacity from Lhc at home. And recently, a long simulation that was also introduced in addition, because it means that you have less I/O. Just a graph to show running jobs over the last month. So 6-track comes in batches, and you see sometimes we don't have many of these, and then volunteers who don't have VirtualBox, they are a bit unhappy, but okay, you contribute to other projects. So 6-track is the dominating one. We have these air peaks of 250,000 tasks that have been up to 450 during the BOINC pentathlon. A few words about our server infrastructure. So we have a server cluster running CentOS. We use 2 up to 3 or 4 load balanced web frontends. And then we have file servers for upload and download. We used to have 3 in service. We added more recently with more load from Atlas with this bigger application. We have a storage backend on CephFS that scales really well. We get much better performance with CephFS than what we used to have in NFS. And then we have additional infrastructure servers for submission, simulation, and so on. And this is on top of the database on all the servers. And we run the latest BOINC server release 1.2.1 since April last year. And that was actually what I had. So especially many thanks to our volunteers, but also to the rest of the community for the excellent collaboration through the years. So it helped with BOINC and so on. So if there are questions, I'm ready to take them.